Okay, so in this video, we're going to talk a little bit more about electric fields. Now, we did some basic grade 11 review last time, that type of stuff, but we're going to look at some basic electric field type stuff. And this is the, a typical type of picture that you can see. They got a little charge in the middle, and there's an electric field coming out of it. It's a positive charge, you can tell, because it is going out. This would be a negative charge because it's being drawn going in. And of course, the idea of where we get the direction from, even though we know all electric fields radiate out from charges, it is based on little tiny particles and what they would do. So if we change it to this, and we don't stop it, there we go. So here we go. We have something like this. So those little dots represent, or could represent, like protons, and those protons are being repelled by the positive charge. And that's why we draw the electric field going out, and vice versa. If it was a negative charge, the little positives would actually go into the charge, and that's why we draw it the way we do. Okay, so this is the type of stuff that you guys have been working with. Now, the tricky part is a lot of the times they are drawn flat, like we draw flat representations, but you have to keep in mind that fields are three-dimensional. They go out in all directions simultaneously, no matter what. They're in three dimensions, not just in two. It's just really hard for us to visualize more than two, and especially draw it on paper more than two. But you have to keep in mind that they do actually radiate in all directions at all times. Even if we go back to the field lines, those field lines go out in all directions simultaneously and radiate out from the object in all three dimensions. The fields are three-dimensional. Okay, even if the setup becomes a little more complicated and fancy schmancy, it's still always a three-dimensional field. For example, here we have two charges. We've got a positive charge and a negative charge, and we've got the fields wrapping around and going across. And even if we move them apart and stuff like that, there we go. We can even do it in terms of the particles themselves. The particles will go out of the positive and go towards the negative. So there you go. So there's our charges flying around. But we can also do this in terms of field vectors. That's a little bit nicer. All right. But once again, the field is in three dimensions. It's not just in two dimensions. So if we get rid of the slicing effect, there's our field going out in all directions simultaneously. So you just got to try and, it's kind of hard to visualize sometimes for some people, but just try and keep in mind that the fields are not flat. What we're not talking about is like flat things. And it doesn't matter if it's, one charge, two charges, it doesn't make any difference. We can go back to particles. These particles are all over the place representing where the electric field actually is. So again, it doesn't make too much difference what we're doing, but just try and remember that the fields are three-dimensional structures, not two-dimensional structures, and they go out in all dimensions simultaneously, but we draw it in two dimensions typically just to keep things a lot easier on ourselves. Okay. Okay, now we're going to flip back to this diagram here, and I'm going to show you something else. Here we got a couple of charges. Here's a positive charge, the field's going out, negative charge, field's drawn, going in. I'm going to show you something else in terms of fields and a little more the nature of the fields. If we go back to like the classic diagram you guys drew in grade 11, you have a positive charge, you have negative charge. Now to get you to draw the field, you guys would typically draw something like this, which is actually kind of misleading in terms of what is actually going on. The fields don't actually come out like bend around like this towards the negative. That's not really exactly what's happening. This is just more of like a map of the pathway that a proton would take if it actually traveled between them. Now, to sort of show you where the diagram sort of really actually comes from, I'm going to get rid of this or just move this out of the way for now. The fields don't necessarily actually change their shape between the charges. And if we want to draw the field between these two charges, it's more like the fields actually overlap than anything else. The fields actually overlap with each other. This is more of a better way to actually look what's actually going on. So to actually draw the fields as straight lines like this, it would give you, it's hard to tell what would actually occur. So what we do is we then, if we sort of compare to what you guys done before, if I had asked you guys to draw the electric field between these charges, you guys would have drawn something like this, and then you guys would have drawn something like this, something like this. Well, let's pick on this point right there. Well, at that point, there's actually two electric fields. There's an electric field from the positive charge going this way. There's an electric field from the negative charge going this way. The vertical components are basically canceling out, and you're left with a horizontal component like this, which is literally what the electric field is right there. It's going straight to the right. It's actually tangent to the curve. So if we went back to this little guy right here, the field, when we draw the fields like this, it's actually not the actual field, it's the net field at any given location. So right here, the field is going towards the right. Always tangent to the curve is where the thing would actually want to go. But it's a combination of a field going up right and a field going down right. The vertical components are canceling out, which gives us that net field. So that's sort of what's happening when we draw electric fields like this, like you guys did in grade 11. They're the net fields. Those are the net fields, the combination of all the field lines put together, showing how things will actually move, how a positive charge, especially like a proton, would actually move between the charges. So the electric fields don't actually come out of the positive, bend around, and go towards the negative. When you guys are drawing electric field diagrams like this, you're actually drawing net fields, not the actual fields. Okay, so they just stay as straight lines coming from the things. We just draw them like this to make things easier to visualize, see what's actually going to happen, because a lot of the stuff that we do with fields, whether it's gravity, electric, or magnetic, a lot of it is actually based on observations of what things actually do within the fields, because we can't actually see the actual individual fields themselves. Okay, so that's a little bit more the background and idea of what you guys are actually doing when we are looking at electric fields. Both the whole idea that they are actually three-dimensional, as well as when we draw field diagrams, those are the net fields that are actually being drawn, mostly out of just convenience and to make things easier to visualize. Okay, next I want to show you guys something else that we can incorporate that you guys have taken already before, and see if we can sort of expand on your knowledge in this stuff as well. This is the typical setup you guys have worked with: parallel plates, uniform electric field, charge going from one side to the other, F equals MA, F equals QE, all that kind of stuff. And we've also incorporated in previous video applying some of your more fancy kinematic equations. Well, we can incorporate some other mechanic stuff that you guys have done as well. When that charge goes from one plate to the other, there's actually a force being applied, and it actually moves a distance. Well, when you talk about applying a force over a distance, you put those two things together, you've got work. So the same way we can incorporate your kinematics equations from grade 12 into stuff you guys did in grade 11, we can also incorporate the energy idea into this stuff as well, which actually can make it an awful lot easier sometimes, especially with a parallel plate setup. So for example, if I want to calculate the work for this charge to go from here to the other side, well, work is equal to force times distance. And everything is nice and parallel, so I don't have to worry about cos theta or anything like that. Work is equal to force times distance. Well, to calculate the force in electric field, basic grade 11, that's QE. So that would be Q times E times D. So right there, that is what I can use to calculate work. Now, of course, when you do work on something, you use energy, and that energy goes to certain things. So one of the things that this will do, this QED expression, this work, one thing it does, of course, it turns into kinetic energy, which of course is equal to 1/2 mv squared. So this actually becomes another way to solve basic mechanics questions like this, is you can use work ideas where, the force QE times the distance can give you kinetic energy, which is 1/2 mv squared. And this is the way to calculate speeds of things. You don't have to worry about time. You don't have to calculate acceleration. You don't need any of those things. So you can actually go back to a lot of the grade 11 questions that you guys did and apply energy to them. And you can actually, a lot of the time, you can actually do the question way quicker, way more efficiently by using energies rather than basic VAT, DTV, F equals MA, that type of stuff. Okay, so we'll be practicing with that type of stuff as well. Well, you've got work involved and you've got kinetic energy. Well, what about the potential energy? Well, the potential energy would exist at the very, very, very beginning. That's where it's got the potential energy. And just like the other ones, it would be equal to the stuff that you had before. So you've got, potential energy at the beginning, and this, of course, it allows there to be work done, which then changes to kinetic energy. So all of these things kick in very similar to what you guys have done before. And you can go one way, but of course you can also work backwards as well. So we can incorporate energy ideas into what you guys are doing. Now, this is where sometimes another quantity kicks into the situation as well. If we actually look at this in terms of the energies and work done, it's really common to see the potential energy actually written as QED. Really, really common because that's what the work is done. They're all equal to each other. Now, the thing is, this results in this little charge right here. That charge right there has potential energy. Well, what if we took the charge out? Well, if we take the charge out, there's no longer potential energy anymore because there's nothing there. All we're left with is just what is called potential. There's potential for something to happen. And we can do the same thing in the formula that we do in the situation. If we take the charge out of the formula, the same way we took the charge out of the setup, what we're left with is E times D. And E times D, that right there is what is called electric potential. And the common word for electric potential, that is what voltage is. Okay, so electric potential is often found by doing electric field times the distance. VED is often used to find the voltage. And that's electric potential. And then what you do is you have the electric potential between the plates. You have the voltage between the plates. But it's not actually good for anything. It's not until you actually put something in there that it actually becomes useful. It's not until you actually put the charge back into the situation when it becomes potential energy. The same way if we have our parallel plates, the parallel plates just by themselves hooked up to voltage, they are useless. You can't do anything. They might have voltage, they have electric potential, but until you put the charge in there, then you have something useful, then you have potential energy. It's sort of like if you take your electrical outlet on your house, you've got the plug and basic electricity, there's 120 volts on there, that is the electric potential right there. The electric potential in the plug is 120 volts. What's it good for? Well, it's good for absolutely nothing because nothing's connected to it. Once you actually take a plug that is connected to something, whatever you're going to use, your TV, your laptop, whatever it is, once you actually take that plug and attach it to this, once you actually attach charges that can be used to the actual plug itself, then it becomes useful. So you got electric field, you've got plates, you can have electric potential, you can have voltage, but not until you actually put a charge into the plates. Then that charge can have potential energy. When it has potential energy, work can be done, and that work can then give the charge kinetic energy. Okay, so this may seem like a little bit of a mess right now, that kind of stuff, but we'll work with this a little bit in the next video, and we'll see how all this stuff sort of fits together, pieces together, because using work and energy is a fantastic way to work with charges in parallel plates.